Alright, so the first theorem of Laplace transform that we're going to discuss is called as the derivative of t transform. So the theorem states that if Laplace of the function f of t is equal to f of s, then for n, so which are what do you call that? It's not whole numbers, natural numbers. So natural numbers mean counting numbers 1, 2, 3, 4, 5, 6, 7, so on, starting from 1. Those are called as natural numbers. If we Laplace t to the power of n, so which is multiplied by any function, so the outcome is going to be negative 1 to the power of n d to the n f of s over the s to the power of n. So first of all, so let's have a look of what does this supposed to mean. Alright, so if you remember, so if we have, for example, if let's say if I'm going to use y and x. So if I have dy over dx, so this means that how many times do I differentiate? Once. So this is actually being differentiated once. So y is differentiated with respect to the variable x once. And if I were to write d square y over dx square, so this over here is an indicator that I differentiate twice. And of course, so if it's to the power of 3, so it means that I actually differentiated 3 times. So that is basically the same idea of what we have right here. Okay, so what happened is that we're going to differentiate the function f of s. So this is what we're going to differentiate with respect to the variable s, and the number of n right here is going to tell us, so how many times do we have to differentiate the function f of s with respect to s. So that is the meaning of that format there. So let me clean this first. Alright, so what happened is that, first of all, when you come across this theorem, so first we are going to identify what is going to be the value of n. So what is going to be the n value? And the value of n is going to determine two things. So the first thing is that it's going to determine what is going to be the power of negative 1. So if it's t to the power of 2, meaning that it's going to be negative 1 to the power of 2 as well, right? And the second implication is that it's going to determine how many times do we have to differentiate the function f of s. So that will be the two implications. Let me repeat that again. So the first is that it's going to determine what is the power of negative 1. And the second implication is that it's going to determine how many times do we have to differentiate the function f of s. Alright, so after we have identified the value of n, so anything else aside from n in t to the power of n in the function, so will be defined as f of t. So what we're going to do with f of t is that we are supposed to convert that to f of s, and of course converting f of t to f of s is going to be through Laplace transform. And after you have obtained f of s, so you have to put them together according to these theorems right here, differentiate, simplify them, and that will be the outcome of the Laplace transform. So let me show you again before we start with the example. So when do we use the derivative of the transform? So there will be two keywords. The first keyword is that when it involves products of function. So the second keyword is that when one of the function involved is a t raised to some power of n, which is a natural number. For example, so if I were to have Laplace of t to the power of 3 cos of t, so yes, so this is going to be derivative of t transform because I have t to the power of 3. And of course, because of t to the power of 3 right here, so meaning by I have to differentiate 3 times. So that is going to be quite a calculation right there, having to differentiate that 3 times. And then, for example, let's say if I have Laplace of t exponential of t. So when you come across cases like this, I've shown you for the previous theorem as well. So you have two choices. So either you can use the first shift theorem because of the exponential. So it is possible to use the first shift theorem. And because of the t to the power of n, so you can also use derivative of t transform. So that is also possible. And either way, no matter what theorem you use, so the outcome is going to be exactly the same. Alright, however, okay, let me give you an example. So let's say if I have Laplace of t to the power of 10 exponential of t. When you come across something like this, so please, for the sake of your sanity and mine, so please do not use the derivative of t transform. Do not use this t transform. Right, so instead please use the first shift theorem, because the reason is if you were to use the derivative of t transforms, let's have a look at the power of t. So this t to the power of n, sorry, is t to the power of 10. So meaning that n is equal to 10. So meaning by, if you use the derivative of the transform, you have to differentiate this 10 times. So please do not go through those kinds of like, what we call that, complication. So instead of like using derivative of the transform, please, so the option is for shift theorem, definitely. No need to think further about it. So using derivative of the transform is definitely not a clever choice. Alright, so let's have a look at differentiation. So basically, before we start, because there will be differentiation involved, so let's revise a little bit on your differentiation, so that later you won't get stuck at trying to differentiate when you come across Laplace transform or derivative later. Alright, so now I'm going to start with a very simple function. So d over ds of 2 over s squared plus 3. So the key point is that every single time before you started your differentiation, so count how many s are there in the function. So here I figured that there's only one s right there. So instead of having to use product rule or quotient rule, so we can actually use the chain rule and differentiate this easily. Okay, so but first I'm going to have to change the form. So I'm going to write this as d over ds of 2 multiplied by s squared plus 3 to the power of -1. Again, so there is only one s right there, so no need to use product rule, quotient rule. We can do that directly. And how we're supposed to do so? So the idea is going to be the same as what you have done, like the usual differentiation. So -1 goes to the front, multiplied by 2, so I'll end up with -2. So this is going to be s squared plus 3 to the power of -2, because when we differentiate, the power become -1. Okay, but however, so the additional thing that you have to do will be, so you have to differentiate the inside of the bracket as well. And for this case, when you differentiate s squared plus 3, so you will end up with 2s, and this is going to be -4s over s squared plus 3 to the power of 2. So that will be the outcome. Again, I'd like to remind you, when there is only one s, there's no need for you to use quotient rule or product rule. That's just a waste of time. So you can do that directly, but you have to know the correct way to do it. Alright, so now for the second example, so the difference is that instead of having one s previously, so I have more than one s in the function. I have one at the top, one at the bottom. So automatically, for this case, it is not possible to do direct differentiation. And for the differentiation, there are only two ways. There are only two rules, which is product rule and also quotient rule. And actually, for this case, so both methods are actually possible. Okay, so let me start with the quotient rule. Right. So quotient rule states that if I have a function in terms of d over ds of u over v, if you wanted to use this, you have to memorize the formula, and the formula is not given. So the outcome is going to be u prime v minus v prime u over v squared. Remember, when you use quotient rule, the function at the top is always going to be u. So the function at the bottom is always going to be v. So it cannot be the other way around. And the formula is always that you differentiate u first, minus, then you differentiate v, right? So do not change them. Automatically, if you change them, your calculation will be wrong. Okay, so now let's start with apply quotient rule to our function. So I'm going to have d over ds of s over s squared plus 3. So therefore what happens is that at the top right here, this is going to be my u function. My v function is going to equal s squared plus 3. So when we apply the quotient rule, so when we differentiate s, I will get 1. So multiplied by v, that is going to equal s squared plus 3. So minus, so differentiate v, I will get 2s. So multiplied by u, that will be s. And that will be over s squared plus 3 raised to the power of 2, my v squared. And you might want to simplify this a little bit instead of living like this. So I will end up with s squared minus 2s squared. So that will be 3 minus s squared over s squared plus 3 to the power of 2. So that will be the outcome. So when we use quotient rule. And as I mentioned just now, so instead of using quotient rule, so it is also possible if you want to use product rule. For example, if you don't memorize the formula for quotient rule, but you memorize the formula for product rule, you can also make this in terms of a product. So let me put this as product rule. Right, so according to the product rule, if you have a function of d over ds, you wanted to differentiate the function of u multiplied by v with respect to s. So the outcome is going to equal u prime v plus v prime u, or it could also be the other way around, which is v prime u plus u prime v. For the case of product rule, it doesn't matter which one of this comes first because it's a plus. However, for the case of quotient rule, it matters because of the minus right there. Right, so do not interchange them for quotient rule, but for product rule, yes, it's possible either way. However, if you wanted to use product rule, it has to be in terms of a product, so you have to change your function a little bit. So make it in terms of a product of s being multiplied by s squared plus 3. When you bring that up, it's going to be s squared plus 3 to the power of -1. And from here, we identify that this is going to be u and this is going to be v, or it could also be the other way around. It doesn't matter. For product rule, doesn't matter. But for quotient rule, at the top is always u, at the bottom is always v. So now let's apply product rule. So let's say I'm going to use this one. So u prime, so when I differentiate s, I will get 1 multiplied by v, that is going to be s squared plus 3 to the power of -1. So plus, so now I'm going to differentiate this part right here by using the chain rule, as what we have done previously. So this is going to be negative, so I'm going to end up with s squared plus 3 to the power of -2, and I have to differentiate the inside. I will end up with 2s, and that is actually my v prime, and I have to differentiate to multiply by u, which is given by s. So if I were to simplify this, I will end up with 1 over s squared plus 3, so minus 2s squared over s squared plus 3 to the power of 2. So basically, if I were to equate the denominator of both of this, I will end up with exactly the same answer that I get from the quotient rule. So basically, if you use quotient rule or product rule, so both of them should give you exactly the same answer. But just leave it like this, so no need to equate the denominator. So just that the form will be different. If you use product rule, just leave until here. But if you use quotient rule, then your answer is going to look like this. But both of them are the same, so it doesn't matter. Okay, so that will be on quotient rule and product rule. So now we can move on to our example. So we're going to start applying what we have discussed. So here I'm going to start with the first example. So I'm going to find the Laplace transform of t sine of 3t. And because I have t right here, so being multiplied by function of sine 3t, so automatically this is going to be derivative of 3 transform. So first of all, what we're going to do is we're going to identify the value of n, because this is t to the power of 1, so it's going to be n is equal 1. So anything else aside from n, aside from t to the power of n, is going to be defined by f of t, and for this case is going to be sine of 3t. And as I have explained to you before, so this will be converted to f of s, which is simply going to be the Laplace of sine 3t. And by using the Laplace table, this is going to equal 3 over s squared plus 9. So please make sure you have your Laplace table for you for this, for the Laplace transform chapter. So I strongly encourage you to print it out and have a physical copy of that. So that's going to be easier for you to refer to instead of having a soft copy. Right, so now that I have all the components, so I'm going to put them together according to the theorem. So I'm going to write that. So according to the theorem, if I have Laplace of t sine of 3t, so that is going to equal -1 to the power of 1, because my n value is equal 1. And how many times do I have to differentiate? Once, because the value of n is equal 1. So I'm going to have d over ds of f of s, which for this case is given by 3 multiplied by s squared plus 9 to the power of -1. Right, so now I have to differentiate, and for this case, every single time you wanted to differentiate, please check how many s are there in your function every single time. Right, so here I have 1 s right there, so I can do that directly. So this one, just copy it down, -1. So when I differentiate this, -1 goes to the front, multiplied by 3. I'll have -3 multiplied by s squared plus 9 to the power of -2. And when you differentiate the inside, you will end up with 2s. And when I simplify this, so I will get 6s over s squared plus 9 to the power of 2. So that will be the outcome. Alright, so you have to differentiate, and whatever that you get, don't forget to multiply by the negative 1 to the power of n at the front. That will be the outcome of the Laplace transform. So that is my first example. So my second example, so now instead of t to the power of 1, so I've changed that to t to the power of 2. The idea is still going to be pretty much the same. I only just want to show you the notation. What happens if you have to differentiate more than once? Right, so obviously for this one, my n value is going to equal 2. My function f of t is going to equal exponential of 7t. When I convert this to f of s by using the table, I'll have 1 over s minus 7. Right, so now I have all the components, so I'm going to start putting them together. So Laplace of t squared exponential of 7t is going to equal negative 1 to the power of 2. My n is equal to, how many times do I have to differentiate? That will be twice. So I'm going to have d squared ds squared of the function 1 over s minus 7. Okay, so the good thing is that when you have negative 1 to the power of 2, that is simply going to be 1. You don't have to bother with that anymore, and all you have to do is differentiate this twice. And how do we write the notation of having to differentiate that twice? Alright, so the first differentiation is going to occur in here in the square bracket. So first I'm going to differentiate s minus 7 to the power of negative 1. So this is where the first differentiation is going to occur, and then I'm going to differentiate that again. The outcome from the first differentiation has to be differentiated again, so that is why I have another d over ds. Okay, so now just copy it down, the one outside, and now let's start differentiating what goes inside here. Remember, I told you just now, every single time you have to differentiate, count how many s are there. So there is only one. So I purposely choose a simple one for the example because I don't want you to get confused between differentiation and the concept. Because when I teach you ODE, I wanted to deliver you the concept of ODE. I'm not here to teach you differentiation. So you should know that already. That is from your prior knowledge. Alright, so when I differentiate this, because there is only one s, I'll end up with s minus 7 to the power of negative 2 multiplied by 1. So that will be the outcome. And then I have to differentiate this again. So again, I check how many s are there, still 1. So therefore, I don't have to use quotient or product rule. I can differentiate that directly, for which I'll get negative 2 multiplied by s minus 7 to the power of negative 3 multiplied by 1. And of course, if I simplify this, I'll end up with a negative 2 over s minus 7 to the power of 3. So that will be the outcome. When I differentiate this, I should get a negative right here. So this is actually supposed to be negative, and this is supposed to be positive. Sorry about that. So change that, because when I differentiate for the first time, so I'm going to have to bring the negative to the front. So this is my negative. So it's going to be negative s minus 7 to the power of negative 2. And when I multiply these two together, so I will end up with the positive 2, s minus 7 to the power of negative 3. So that's going to be positive of 2, right? Not a negative one. Okay, so this is going to be the final outcome of the Laplace of t squared exponential of 7t. And of course, as usual, so I have put these videos together with the notes. So I prepared the notes. And there is exercise that you can try. So I have a bunch right here with the solution as well. But question number 3 is a bit special. So this is actually a previous test question. So there are actually multiple ways of solving this. There are in fact 6 possible ways of trying to find the Laplace transform of this. It doesn't matter what method you use. All of them are going to give you exactly the same answer. Let me give you an idea. How do you pick which theorem? So pick the theorem that is going to be easiest for you. For example, here, if I were to consider the fact that I have t, e, and u, I can use like mostly all theorem. This is going to be derivative of t transform. This is going to be first shift. This is going to be second shift. But I personally think that first shift theorem is the easiest. So therefore, if I were you, I would start with first shift theorem first. But you don't have necessarily to do so, so it's up to you. So pick which one that you're most comfortable with and the easiest for you to try. Okay, so either way, you will get the same answer at the end. Right, so give it a go, and the solution is here for you to check.